On last lectures, we had a stochastic differential equation with smooth coefficients on RD, and we proved that such equation generate a stochastic flow of homeomorphisms. And yesterday we showed that actually this stochastic flow is generated by some random dynamical system. Also, we gave some examples of interesting stochastic flows of non-homeomorphic random mappings. In particular, we discussed flows in which two trajectories that start from different points can, in finite time, reach the same point, which we call coalescence. So the question is how to describe such stochastic flows, and is it possible to define corresponding random dynamical systems? The main features of stochastic flows generated by stochastic differential equations were the following. So phi st was the flow of random homeomorphisms. By flow, we mean a collection of mapping that are connected by the evolutionary property. Also, if we consider disjoint segments of time, like from t0 to t1, from t1 to t2, and so on, then mappings act independently. And also, the distribution of the random mapping depends only on the length of the interval on which this mapping acts. In this sense, we can understand the stochastic flows of mappings like a description of a fluid evolution in a stationary random media with independent increments. If we fix S and X, then the function phi stx as a function of t can be viewed as a trajectory of a point that was thrown into the flow at time s at point x. So we can imagine that we throw an uncyclable point into some fluid with random perturbations, and then this process in t describes the evolution of this point. So one natural way to describe stochastic flows is, in some sense, to look at all these evolutions in the following sense. So assume for now that we have a nice stochastic flow, meaning that it is continuous, it is a stochastic flow of homeomorphisms, and let us fix endpoints in the state space. Yeah, so X is an n-dimensional vector, and we can consider the following quantity. So Pn xb, it is the probability that under the action of the flow, endpoints x1, xn in time t will arrive to some Borel set B. If n is equal to 1, then let this be time 0. Have the flow of mappings. So the probability P1 means that at time t we fix some set B, fix some point X, and look at the probability that under the action of the flow, the point X will arrive to the set B. It turns out that functions P and T are transition functions of Markov processes. This follows from the flow property and from independence and stationarity of distributions of phi. Indeed, if we look at probability Pn t plus s, yeah, this is the probability that x1 xn in time t plus s will be in the set B. Then we have a flow property, so each mapping phi 0 t plus s we can write as a composition, phi 0 s and phi s s plus t. After that, we compute the conditional probability given phi 0 s. I didn't write expectation here, it must be also expectation. And by independence, the conditional probability is computed as follows. We just fix this, we just fix values of phi 0 s of x. Then the probability is equal to P and T with the starting points phi 0 s of x. And then when we take expectation, we get exactly the Chapman-Kolmogorov equation for Pn. So to a stochastic flow, we associated a family of Markov processes, which are called endpoint motions of the flow. And these Markov processes, they satisfy two natural conditions. The first one is consistency. So if we take k indices from 1 to n and consider the mapping p, consider the mapping pi that takes n points and return k points with indices xi1, xik. Then the transition function Pn starting from x, the probability that we will arrive to the pre-image of a set B is equal to the probability that k points starting from xi1, xik will arrive to B. This is a very simple property because on the left side we have the probability that phi 0t x1, phi 0t xn belongs to the pre-image of B. But this is exactly the probability. Let me just change it here, that xi1, that a trajectory started from xi1, xik in time t arrive to the set B. So this is very similar to the consistency of finite dimensional distributions of a stochastic process. And the second property is also very natural. If we look at the two-point motion of the flow, so the motion of two trajectories that started from the same point x, then they will always be equal, because we will look at the motion of the process phi 0 tx, phi 0 tx. In other words, the transition function P2 that starts from diagonal always stays on the diagonal of the state space. Okay, so we have a consistent coalescing sequence of transition functions. In some sense, it is possible to go backwards. So start from a consisting coalescing family of transition functions and try to define a stochastic flow. This can be done in the following sense. There is a quite old result that states the following. So we have transition functions Pn, they are consistent, coalescing. Then on some probability space with a group of measure preserving transformations theta, so it's like a group of shifts, we can construct a family of random elements, of random mappings of M, such that the flow property holds if we fix endpoints x1, xn, then the process phi s plus t that starts at these points is a Markov process with a transition function Pn. On disjoint time intervals, mappings act independently, and we have even equality that the mapping that acts from S to T coincides with the mapping that acts from 0 to T minus S, but evaluated at the shifted noise. So this looks very much like random dynamical system. And then we can ask, so what else we need if we can reconstruct the flow from transition functions? However, if we look closer at this result, so phi st is a random element in the space F, and F is the space of all mappings of M. So this is the product M to the power M. Not writing somehow. Okay, so F is the space of all mappings of M equipped with a cylindrical sigma field. And it is known that this is not a very good space to define processes on. In particular, in this construction, okay, I'm sorry, I don't know why it is not writing. Let me share again. Okay, so in this construction, if we look at one random mapping phi, it's not and this is quite strange because here we substitute random elements into random mappings. Yeah, so here instead of x we substitute phi rs of x. So we substitute a random element into a non-measurable random process, but still we get a random element because of the flow property. But this limits the possible actions we can do with such a stochastic flow. So in some sense, the only things that we can substitute in these random mappings are values of the random flow. So we cannot consider the action of the flow at some more complicated object than just trajectories on the flow, on which the action is trivial because of the flow property. So one issue with this construction is that we don't get measurability even in X. Also, we don't get measurability in S and T. And this group of measure preserving transformation, it is also a non-measurable group. In other words, we don't get a random dynamical system, because in the definition of the random dynamical system, we need a measurable group of measure preserving transformations, and the dynamical system itself must be at least a measurable map. Okay, so we have an existence of the flow, but this result gives a flow with a bad properties as functions of S, T, and X. There is a more recent approach in which F is the space of all measurable mappings. So in this approach, we want to construct the stochastic flow that must consist of measurable mappings in X. So we will have random mappings from the flow will be random elements in the space F. To do this, an additional assumption is made that transition functions Pn are failure transition functions. So once we have such sequence of failure consistent coalescing transition functions, then on some probability space, we can construct a family of random mappings, a family of random measurable mappings. However, in this construction, we don't have the flow property that holds simultaneously for all R, S, T, and X. This result only gives crude flow property in the sense that equality here holds almost surely, but the exceptional set can depend on R, S, T, and X. And the rest is the same as in the previous theorem. So finite point motions are Markov processes with the transition functions Pn. On disjoint segments, mappings act independently. And again, this stationarity property, it holds almost surely. One more feature of this construction, that the probability space it can be chosen to be a separable probability space, in the sense that L2 is L2 over this space is a separable Hilbert space. So these are two, I think, the only two results that consider the construction of the general stochastic flows. And we see that in neither of them we get a flow with nice properties, and we don't get random dynamical systems. Now my aim will be less ambitious, so we will look at the one-dimensional case and add some more assumptions on transition functions to get the true coalescing stochastic flows and to get random dynamical systems. Assumptions don't look very restrictive, so the first additional assumption is a sufficient condition for continuity. This is the probability that in time t, the trajectory will deviate from initial state by epsilon, and this probability is O small of t. It is known that under this condition, our finite point motions will have a continuous trajectories. Okay. Second assumption is the estimate on the meeting time. We will assume that for every positive t, there is some continuous increasing function m, such that the probability that two trajectories that started from points x and y did not coalesce by time t is bounded by the increment of function m. And one more assumption, it's actually, it can be removed, but we will assume it for simplicity that one point transition functions have no atoms. Okay, so we have a sequence of Feller consistent coalescing transition functions with these additional assumptions, and we will prove that we can construct a flow, and we can construct it via random dynamical system. In the proof by Pn of x, I will denote the distribution of the Feller process that corresponds to transition function Pn. As we discussed yesterday, for coalescing stochastic flows, it is not clear what to take as the underlying metric dynamical system. So first of all, I want to define the proper probability space on which the random dynamical system can be constructed. Okay, so to compare with what is done in these results, here the probability space is the space of all families of mappings phi stx that satisfy the flow property. And all issues with measurability come from the so this space is too big to give the process with a nice properties. And this space is similar to what is done in Kolmogorov theorem when we construct the process on the space of all functions. So the idea is to make the probability space smaller, and this can be done in the following way. So now, by the probability space, I will consider all families of continuous functions with properties 1 to 4. So this notation means that every element of the probability space is a collection of continuous functions. These continuous functions are indexed by s and x, and for each s and x, we have a continuous function from s infinity with a starting point x. So it means that for each s and x, this is continuous and starts at x. Okay, and we assume that omega omega consists of such families omega small, for which, first of all, the flow property holds. Second is so-called denseness of the past. This property means that we fix time s and look at all continuous functions from a family that started before time s. And their values at time s must be a dense set. Okay. Next property is I call it regularity at fresh points. It means that if the point x is not the image of some trajectory that came from the past, then at this point the mapping from the flow is continuous from the right. And the last property is immediate coalescence. So if we consider the trajectory that started at time s from point x, look at its value at time t. So this is t omega stx. Then we assume that at time t, this trajectory have met some other trajectory started from ry, and y is a fresh point. So these are assumptions on our probability space. I define it in such a way to capture main features of the coalescing stochastic flows. In particular, this space omega doesn't contain any flow of homeomorphisms, because for a flow of homeomorphisms, there are no fresh points. At every moment of time, trajectories that came from the past, they fill all the real line. One can ask if there are such flows that belong to the space omega. One can even construct it by hand. So this is an example of the flow from the space omega. Function g is some homeomorphism from 0 infinity to 0 1. Points that have points that correspond to integer values of x are fresh points, and at each such point we define a trajectory using the homeomorphism G, and we shift it by the time t minus s. This flow is indeed an element of our space of flows, because at every moment s, trajectories from the past, they exactly fill all real line except integers. So it is a dense set. And also every trajectory, in fact, starts from the fresh point. Okay. We can equip the space omega with a cylindrical sigma field, which means that it is the smallest sigma field under which all such mappings are measurable. And an important feature of this space, that the mapping that the mapping omega stx, it becomes measurable in all variables in s, t, x, and omega. This is very similar to what we had in the smooth case. In the smooth case, we had omega, the space of continuous functions. And we know that on this space, the mapping, the mapping that computes value of continuous function at point x, it is jointly measurable in x and omega. It is even jointly continuous. And we don't have this property when omega is the space of all functions. So in the space of all functions, such mapping is not measurable. Okay. Now we will show why this lemma is true. But before that, we have a consequence. So let us define the shift just by shifting arguments of the flow, and define phi as the mapping from the flow that acts from 0 to t. Lemma implies that both theta and phi are measurable, and phi is a perfect cocycle over theta. Indeed, if we write phi t plus s omega, then this is just omega 0 t plus s. Yes, by our construction of the space, this is the composition, and omega s plus t coincides with omega 0 t, but let's better write, it coincides with theta s omega 0 t, composition omega 0 s. So we have like a first step to get a random dynamical system. Okay, now let's look at the lemma. To prove the lemma, we need to show that such an event is measurable in s, t, x, and omega. Event means that the value of the flow if we get the representation of this event in the following form, we will get that this event is measurable. I mean, this event is measurable as a set of all s, t, x, and omega. Because this gives us like a countable union, and all these properties, they are measurable in omega s t and x, because here you see that if such a representation is possible, then we take s and x from the flow, we take it into the we take s from the initial condition to the future time of the flow, and we take x outside from the flow. In omega s, we have measurability because of continuity. Okay, so the representation we want is the following. There is a trajectory that started at some rational point before time s. At time s, this trajectory was above x, and at time t, it was below c. And it is easy to see that the condition is sufficient to our initial event, because omega st of x, by the flow property, it is equal to by the flow property, it will be less or equal than omega st of omega ps of u. Here it is important that the flow is on the real line, so it preserves the order. Then this is omega pt of u, and this is less than c. So the condition is sufficient. Why it is necessary? To prove necessity, we consider two cases. Case one, assume that there is a trajectory started from ry, that at time s it was above x, and at time t it was below c. Since we have the denseness of the past, we can find a trajectory that was between x and this point. Actually, we can find two trajectories that were between x and this is omega rs of y. And we can take a rational point between these two trajectories. Then what we can say about the flow that starts from this point pu? At time s, it must be bigger than x, yes, because it is bounded from above by this function. And at time t, it must be below c, because it is bounded from above by the trajectory ry. It means that we have this condition. Okay, it is proved in the case when some trajectory was above x at time s and below c at time t. But what if there are no such trajectories? So this is case two. Case two means that if a trajectory is above x at time s, then it must be above c at time t. If this is a fresh point of the flow, I mean, if this point didn't come from the past, then we have right continuity. So by right continuity, we will have a trajectory that is above x at time s and below c at time t. But in case 2, it is impossible. Hence, the point Sx is not a fresh point, so it arrived from the past. Moreover, it arrived from some fresh point from the past. And we have right continuity at this fresh point. And by right continuity, if the point z is close to y, yes, then at time t, this trajectory must be below c. But then this trajectory that starts from z, it cannot be bigger than x, so it must be equal to x. Now we can take the rational point between trajectories that started from y and from z, and it must arrive at x at time s and be below c at time t. So again, we get the sufficient condition. So in case 1, we proved that this condition holds with a strict equality, and in case 2, we proved that the condition holds with equality. In case 1, it is strict inequality. In case 2, it is equality. As a result, we obtained the space of coalescing flows with a nice measurability properties. Now we need to build the probability measure on this space. And to do this, we will define a random element in this space with a proper distribution. First of all, note that by Kolmogorov's theorem, we can construct the countable family of trajectories of the flow with the needed distributions. Okay, and now let's look at the properties of this countable family. Processes y, p, u, they start from all points with rational coordinates pu, and each this process, it is a Markov process with a transition function p1. If we look at 2 processes, then it will be a 2-dimensional Markov process with a transition function p2 and so on. Then we need the following properties of processes y. So first of all, y, every process ypu never hits the starting points of other processes. So this is a consequence of absence of atoms in one-point motions. And also it shows that all starting points of processes property that when 2 processes meet, they coalesce. This is a consequence of our assumption on transition functions on 2-point motions. The third property is a denseness of the past. that shows that if we look at all processes y that started before time s, their values at time s will form a dense set. Next property says that if we take two moments of time, s and t, take here an interval AB, and look at all processes y that were at time s in this interval, and look at values of these processes at time t. It turns out that at time t they form a finite set. So a lot of meetings happen between times s and t. We get only a finite set of values at time t. And one more condition is the right continuity. Yes, the even uniform right continuity. Okay, so now let's check this lemma. We already discussed conditions 1 and 2. So what about property 3? This property is a consequence on our assumption on one-point motions. In fact, this condition can be strengthened to the following. We look at the probability that one-point motion deviated during time t deviated from x at least by epsilon, and then this probability is so it converges to 0 faster than t. So it is a simple consequence of this condition. I missed t here. Then we can consider a rectangle with rational vertices divided into two parts, and consider the partition of this rectangle in such a way that the probability that trajectory y that starts from this point deviated by epsilon, let this be epsilon, yes, deviated by, in my notation, this is the delta. So the probability that trajectory starts from this point deviated by delta from initial point during this small segment of time is less than the length of time divided by 2 to the power n. And if we consider these events, we will get approximately kn events, and their probability is of order 1 over 2 to the power n kn. It means that with probability 1, none of these events happen. So all trajectories y that started from points of partition stayed inside the rectangle. It means that if we fix any time s, fix any interval on the real line, construct a rectangle of this type, with rational vertices. Then what we showed is that trajectories y for small enough partition, they stayed in this rectangle. In particular, they have intersected the interval at time s. And this exactly means that the trajectories that came from the past form a dense set. Okay, property 4 follows from estimates on the meeting time. So if we choose n endpoints in the segment AB and look at trajectories that start from these points at time s, and we denote by dn the number of trajectories that didn't coalesce by time t. Then we can write that expectation of dn is equal to expectation of dn minus 1. Yes, so number of the trajectories that remained when we consider the start from u1 to un minus 1, and plus 1 or 0, depending on have the last trajectory coalesced with the one below it or not. So expectation of dn equals to expectation of dn minus 1 plus the probability that processes started from un minus 1 didn't coalesce during time t minus s. And we assumed that this probability is estimated by the increment of continuous function m. If we proceed with this estimate, we will get sum of increments of m, which is bounded by 1 plus the increment of m on AB. And this bound is uniform over all starting points. So that we can take supremum over all possible starting points and still get a bounded random variable, which means that at time t we can have only finite number of points left. Okay. After we checked properties of the skeleton, we can define the flow. And the flow is defined by approximation from above. So at every point x, we look at the infimum of all processes y at time t that were above x at time s. Actually, there are two possibilities. If the point x is already like here, yes, if it is already the value of y, then the infimum will also be equal to this trajectory y. If x is not on any of points, if x is not on any of processes y, then we take the limit from above. And as an exercise, I suggest to verify that all realizations of our space of flows. Actually, all four properties in the definition of omega, three of them we already verified for y. The one that we didn't verify is the flow property of psi. However, if we take r less than s less than t, and let's say y is equal to psi rs of x, then since during time from r to s, all processes y coalesced into a finite number of points, then y must be equal to the value of some process y capital at time s. Let's write it as ypu of s. But then, as we noted, if we apply psi to this value, we will necessarily get ypu of t, and this is psi rt of x. So this proves that psi is indeed a flow. Why it has the right finite point motions follows from, again, from the construction of our approximation. Now we don't have a continuity of psi in this special variable, but we defined psi as in such a way that these points ym, they approximate x from above, and simultaneously psi st of ym approximate psi st of x from above. Because if x is if x belongs to the trajectory of the process y, then simply ym will be equal to x for large enough m, and psi st ym will be equal to psi st of x. And if x is not on the trajectory of y, then psi st is the limit from above. So this finishes the construction. Actually, we constructed the random dynamical system that that gives us coalescing stochastic flow. Let's apply it to the so-called generalized Arati flow. I recall that Arati flow consists of Brownian motions that move independently before meeting and coalesce at the meeting time. We can extend it to the following system. We consider solutions of such stochastic differential equation that move independently before meeting time and coalesce at the meeting time. And from our results, such flow exists. In fact, the only thing we need to verify is the estimate on the meeting time. I wrote the estimate on the meeting time as the following inequality. This can be refined to the so-called local estimate. So in this probability, we assume not only that trajectories didn't coalesce, but we can also assume that they stayed in some fixed segment. And this will be enough. Okay, so now let's consider independent solutions of the SDE. Assume that A and B are Lipschitz and B is strictly bigger than 0. Using these localization arguments, we can assume that B is separated from 0. Now, if there is no drift, then the difference of solutions is a continuous martingale, and its quadratic variation is bounded from below by quantity, let's say 2 delta squared t. The continuous martingale d can be written as some Brownian motion from the quadratic variation of this martingale. So the meeting time of d is bigger than t, is bounded from above by below by the time that Brownian motion that starts from y minus x doesn't reach 0. So it is bounded by some constant times y minus x, which is exactly what we need. If there is drift, it is well known that the transformation of the space by the function m removes it. And we again get an estimate on the meeting time. Actually, this function m is exactly what appears here. So we get the existence of a flow of, this is a generalized variety of flow that consists of such diffusion processes independent before meeting time and coalescing at the meeting time. Okay, the next question I want to address is to consider dual flows. I will just in a few words explain the definition, and we will continue next time. Dual flows are backward flows, meaning that they are indexed by Ts when S is less or equal to T. So it can be understood as the flow that acts backwards in time. So psi tilde Ts acts from time S to from time T backwards to time S. Backward flow is called dual to the flow psi if we have this inequality for all st, x, and y. This inequality means that these two brackets cannot have different signs. It is impossible that one is positive, other is negative. It means that trajectories of the dual flow do not intersect trajectories of the flow psi. If we look at psi st of x as a function of x, since it is a flow, it is an increasing function. And there are two, this function as a function of x can be not invertible. But there are two natural pseudo-inverse functions, v plus and v minus. So v plus is continuous on the right in y, and v minus is continuous on the left in y. So one can show that a backward flow is dual if and only if it is if and only if its values are between v our aim for tomorrow will be to construct dual flows for coalescing stochastic flows and use them to analyze invariant measures and some other functionals from the coalescing stochastic flow. And I think I finished for today. Thank you for the attention.
Thank you. Maybe some of participants have questions.
Well, yes, I have a question. So you said that there is a result of Arnold and company how to create a perfect cocycle from a crude cocycle. You also said that by the result of Lejeune-Raymond, we can create a crude cocycle. So why we need?
Yes.
So why we cannot combine these two results to obtain everything without extra constructions?
Because in the perfection theorem, we need crude cocycles with values in topological semigroups. So the space F where mappings live, it must be at least a topological semigroup.
Okay.
So there is, and this comparison, this operation is continuous. Lejeune-Raymond have a group of measure. It's not a group. Yes, they have a semigroup of measurable mappings, and the composition is not continuous on this group.
Okay, thank you.
It is even not measurable on this group. So typically mappings from coalescing flows, they don't live in a good topological semigroups to apply this perfection.
Okay, thank you.
Okay, if there are no other questions, then let's have a break.
May I ask a question?
Yeah, sure.
Yeah, so yesterday we had a question about invariant measures for the Ornstein-Uhlenbeck. So I just wanted to ask if this person is here, did he manage to do calculations? But maybe he's not here.
Yeah, I can't see him.
Okay.
Ornstein-Uhlenbeck was also mentioned
if,
in the lecture of Dorogovtsov in this context of stationarity.
Okay, so maybe.
Yeah, so the problem was solved.
Maybe it was asked there.
Not asked, but clarified by Dorogovtsov. So.
Okay, then thank you for your attention.
Then let's meet in 20 minutes.
Thank you.
Yeah.